Okay, today's topic is one of the most important topic in this entire course. It is called spectral analysis. It is also called in different names. Sometimes we call it estimation of power spectral density or spectrum analysis, power spectrum analysis. There are various names which are available actually, but they all mean the same, spectral analysis. Now, before I go into it, let us first make some background and then we will define what is called power spectral density and all those things, okay, and its physical implication and properties and all those things. First, we start with what is called, and again this entire thing will be dealt with not only in the context of analog signals, there is continuous time random processes, but also for discrete signals. In fact, towards the later part, we will be concentrating more on the discrete random processes or discrete random signals and spectral analysis for them, okay, because many sophisticated algorithms are available today to estimate the power spectrum of discrete random sequences, okay, which are of course which one can of course relate to the original spectrum of the corresponding continuous time signals. But anyway, we will not go right now, we will not go that far, because most of the things will not be understood by you now, unless I give a detailed description of what is spectrum and all that. Okay. So, before I go into it, just a couple of results. Okay. One of them possibly I have covered earlier, but I am not sure, and there is nothing wrong in covering it again. It is called Cauchy-Schwarz inequality. Actually, this is a very famous inequality and it applies not only to random variables and all that, it applies to, in fact, it is an inequality which is available in the study of vector spaces. It relates to the norm and inner product of vectors and all that, but we will not go into that. We will confine ourselves to the context of random variables only, that is, we will be studying this inequality in the context of random variables only. But remember, that is only a limited way of looking at Cauchy-Schwarz inequality, its scope is much more. Nevertheless, suppose x and y are two random variables given to you, then this inequality says that if you take the correlation E x y star and call it say R x y, and E of mod x square, you call it sigma x square. If you define this term sigma y square, then this says that if you take the correlation, which in general could be complex, take the mod of that and square, that is less than equal to sigma x square sigma y square, with the inequality that can be either less than or equal to. The equal to valid if x and y are linearly related. If x equal to some k y or y equal to some k prime x, we say that if x and y are linearly related. Okay. Now, you can ask one question here, that if I write x equal to k y, it equivalently means where k is any number, that is, firstly, what is the meaning of x and y linearly related? That is, x is some multiple of y or y is some multiple of x. In that case, we say x and y are linearly related, and we are making the claim that if this is so, if x and y are indeed linearly related, then this inequality actually becomes an equality, otherwise it is strictly less than. Now, you can ask me a question here, that see, once I write x equal to k y, does it automatically imply that y equal to 1 by k x, that is, y also a multiple of x? Yes, but still I am doing it for some mathematical correctness, and you can see that why. Suppose k is non-zero, then x equal to k y or y equal to 1 by k x, okay, 1 by k is then defined 1 by k x, I mean both are equivalent. So, you can say x is a multiple of y or y is a multiple of x, but suppose x is 0 and y non-zero. Okay. You can see one thing, that even if x equal to 0 and I mean in this inequality, suppose x is 0, that is x is 0 random variable and y is non-zero. In that case, the correlation is 0, okay, and sigma x square is 0. So, in that case obviously it becomes an equality, because on the left hand side the correlation between x and y is 0, because x is a random variable which always takes 0 values 0, and on the right hand side sigma x square, there is the variance of or the power of this 0 random variable, that is 0. So, right hand side and left hand side are equal, it is equal. So, 0 equal, so that means when x equal to 0 or for that matter y equal to 0, the equality is valid. This we can see by inspection. Now, does it fall under this category that if x equal to 0 or y equal to 0, x equal to k y? Now, suppose x equal to 0 and y non-zero, we can always say that look, x equal to 0 and y non-zero, why not take k to be 0, a scalar 0 number, then 0 times any non-zero random variable will still give you 0. So, x equal to 0, y non-zero, that is satisfied here. Okay. Just k becomes equal to 0, but in that case one cannot write that if x equal to k y, y is also 1 by k x, okay, because y is non-zero and x is 0. So, now no finite number times 0 gives you another non-zero number. Okay. That is why I write separately that y equal to k prime x, that x equal to 0 case, fine, 0 equal to some scalar 0 times y, this is satisfied. Okay. But the y equal to 0 case, that way suppose y equal to 0, for that y x may be non-zero, k prime is 0, y, so you get again y equal to 0. Okay. Anyway, you can easily see one thing, that if you put x equal to k y or y equal to k prime x on the left hand side, then this becomes an equality. You can see this. Suppose x equal to k y, then r x y, which is E x y star, it is simply k sigma y square. You put k y here, k you take out, y into y star, that is mod y square, and that is k sigma y square. Okay. So, on the left hand side if you square it up, you get k square sigma y square whole square, and on the right hand side, this is on the left hand side, and on the right hand side what do you get? Sigma x square sigma y square. Sigma y square is already present, and what is sigma x square? Sigma x square E of mod x square, and E of mod x square is E of mod of k y whole square. So, mod k square goes out, and again sigma y square. So, again you can see left hand side and right hand side, they are indeed same. Similarly, you can verify that y equal to, when y equal to k prime x, even then the equality is satisfied, and this y x equal to k y or y equal to k prime x takes care of the 0 cases, that is x equal to 0, y non-zero, or y equal to 0, x non-zero, both cases are satisfied here. For instance, when x equal to 0, x is a 0 random variable and y is not, then I can always express that as x equal to k y where k is 0. Similarly, when y is the 0 random variable and x is not, I can write that as y equal to k prime x where k prime is 0. So, these two cases, x equal to k y or y equal to k prime x, takes care of all types of linear relations between x and y. Okay. And whenever this is satisfied, we can see that the inequality becomes equal. Now, we go for the case where x is neither equal to k y or y, nor y is equal to k prime x for any scalar k or k prime, that is x is, and therefore, neither x is 0 nor y is 0, because x equal to 0 case or y equal to 0 case come directly under this. Suppose then we are, I repeat again, we are now talking of the case where x is not equal to k y or y is not equal to k prime x. So, there is no linear relation between x and y, which also means that neither x nor y is 0 random variable. In that case, my claim is that inequality becomes a strict inequality, that is strictly less than, no equal to. That this is the major part of the proof that we consider now. In fact, we can go to the next page. In this case, suppose I consider this x minus r x y by sigma y square into y. Now, r x y by sigma y square, this is a constant, this is not random, this is a constant number, some number you can say k or L or whatever is actually in our case r x y, cross correlation between x y divided by sigma y square, this times y. If I now take expected value of mod square of this, firstly you see one thing, that we are now considering the case where neither x equal to k y nor y equal to k x, k prime x. Okay. Which also means that neither x nor y is a 0 random variable, which also means that sigma y square is non-zero, therefore, strictly positive, and therefore, there is no division by 0 here. So, I can happily write r x y by sigma y square without any problem. Further, x minus this constant time y is non-zero, because that is what I said, that we are now talking of the case where x and y are not linearly related, that is there is no scalar by which if you multiply y you can get x. X minus any scalar times y is always a non-zero random variable for any choice, whatever scalar you choose, because x and y are not linearly related now. Linear relation we cover already. That means x minus this constant times y is not a 0 random variable. So, if you take mod square of that and expected value, that will be strictly greater than 0, there is no question of it is becoming equal to 0. Now, E of mod square of this means E of this quantity multiplied by its conjugate, that is x minus this constant times y times within bracket x minus again the constant time y, but conjugate. Now, if you really do that exercise, it is very simple to see that first terms will be E mod x square, then there will be one term involving the cross term, okay. That is this quantity r x y, or maybe if you are not sorry, if you do not feel comfortable, okay, I am not able to erase that. So, let that be there, okay, or maybe I draw from here. Okay. That means x minus star this is greater than 0. Okay. If you multiply, expand, what you get is E of mod x square, because x star which is sigma x square, and another term you cross term this r x y y by sigma y square times x star, expected value of that. So, that will give you r x y by sigma y square, that will go out into E of y star y x star, that is x star y. Now, I defined E of x into y star as the correlation r x y. Here it is x star y. So, this is a conjugate. Okay, you can also write this as, you can take this conjugate out and put it here in these two places, here and here, okay, which is nothing but r x y star. This is nothing but r x y star. There is one cross term. What is the next cross term? X into conjugate of r x y by sigma square y. Okay. So, that means r x y which can be complex. So, I am putting a star, sigma square is real, no star, and expected value of x y star, which is again r x y, and last term is r x y star divided by sigma y to the power 4 . So, mod r x y whole square divided by sigma y to the power 4 into expected value of y star, that is expected value of mod y square, which is again sigma y square. This entire quantity is greater than 0. Now, you can see one thing, here you get r x y into first term r star x y. So, mod r x y square divided by sigma y square. Second term, third term also r x y star into r x y, again mod r x y square divided by sigma y square, and last term is mod r x y square sigma y square. So, three terms are same, 2 are with minus, 1 with plus. Okay. So, after simplification, then it means sigma x square minus mod r x y squared divided by sigma y square, this is greater than 0, which proves that inequality. If you take this one term to the right, basically it is very simple, you get this. Okay, this is called Cauchy-Schwarz inequality. We have proved it in the context of random variables, but actually its scope is much beyond this random variables. I mean, basically an inequality which you study in the context of vector spaces. We remember, we also said that random variables can be treated as vectors in an abstract vector space, where correlation between two random variables is actually the inner product, that is so called dot product between vectors. Okay. The rule of vector addition, that is just addition of normal random variables, usual notion of addition of random variables, scalar multiplication of random variables, all those were discussed earlier. Okay. And the Cauchy-Schwarz inequality actually is a topic of vector space theory, and that is it can be proved in the general vector space context. Here, for the sake of simplicity, I just did not bring in the vector space concept. I applied all the usual steps of Cauchy-Schwarz inequality purely in the context of random variables. Okay. Now, why this? What follows from this? Two things follow from this, which are important in the context of spectral analysis. So, I just obtained them here. Number one, suppose you are given a random process. For the time being, I will put x a t, or maybe a is not required. Whenever I use the variable t, which stands for time, it will be automatically implicit. It will imply that I am dealing with a continuous time random process. X t is given, it may be a complex valued, but continuous time random process. Suppose it is given. Okay. In that case, in the previous inequality, we had this, right, R x y, that is E x y star. Now, suppose I consider this, that is x t, this is suppose your x in the previous case, and this is your y star, that is y equal to x of t minus tau. Okay. X t is a random variable, that is the sample at a particular time index t, time at a point of time t, whatever the sample, that is a random variable. So, x of t is a random variable, we call it say x, and x star t minus tau, I call it y star. Okay. There is x of t minus tau, that random variable is say y. So, it is star of that. If I consider this, this correlation, which in fact is nothing but r tau, because I am assuming WSS process, say White stationary process. So, this is r tau. I should have written r x x tau, but for the time being I am dropping the subscript x x, because I am not dealing with any other random variable here, random process here. So, r tau by Cauchy-Schwarz inequality, I can then write is less than equal to sigma x square, sigma y square, and for the time being we assume, I am assuming that these two variables x and y, they are not linearly related. That is, the random process is such that no sample is a linear combination of some other samples. It is a purely non-deterministic process. Those processes are called deterministic, where one sample can be written as a linear combination of some other samples, but we are considering a non-deterministic process. So, obviously, no two samples are linearly related, non-deterministic. So, it will be strictly, this will be strictly less than what? Less than what? Sigma x square, sigma y square. What is sigma x square? That is variance, okay, of the process x t, that is E of mod x t square. Because of stationarity, that will not depend on t. So, that you can say R 0, which is real and positive in our case, okay. And again E of, and then sigma y square is nothing but E of mod x t minus tau square, t minus tau whole square. Now, as I told you, because of stationarity, E of mod x t minus tau whole square will also be same as r 0, because the time index does not matter because of the stationarity. So, just a minute, the inequality had square of that. So, r square tau, remember the inequality had square of that, r x y square, mod r x y square. Okay. So, it will be actually mod of this in the Cauchy-Schwarz inequality, mod of r x y whole square was less than equal to sigma x square sigma a square. So, I apply mod on this correlation take square, that is less than equal to r less than r 0 into r 0. So, r square 0. So, mod of this that means you take the positive square root from both sides. So, that means for any non-deterministic White-Side stationary random process, where you have the maximum value of the correlation, autocorrelation, that is at lag 0. For any non-zero lag tau, the correlation value has a magnitude that is less than r naught. Okay, that follows from here. Secondly, so I erase this thing. So, what followed from previous discussion, only that we write, r tau less than r naught. Okay. This we have already obtained. The other thing is, if you now consider again Cauchy-Schwarz inequality, but in this form, expected value of say x t plus tau plus say tau prime minus this quantity time x star t. Second, by Cauchy-Schwarz inequality, it will be less than here, less than always, because I told you there is no linear relation between the samples of the process. So, it is strictly less than, it will be less than expected value of, that is the variance of the first term into the variance of the second term. There is expected value of mod of t plus tau prime minus x t plus tau this square into expected value of mod of x star t square. Okay. Now, what does it imply? This is from the Cauchy-Schwarz inequality. Now, what does it imply? In the left hand side, you consider the first product. This is what x, this is a product. And so, it will give rise to this autocorrelation. But what are the time points? One is t plus tau prime, another is just t. So, lag is tau plus tau prime. So, it will give rise to nothing but r, you can say r x x, but I am dropping that subscript x x. So, r of what? Tau plus tau prime. In the other case, what it will give? It is just r tau. Okay. And this is, you take the mod of that, of course, mod square. So, that means left hand side gives you tau plus tau prime minus r tau square, that is less than. Now, here the second term mod of x star t is same as mod of x t, and e of that square of that mod x t square, e of that is simply r 0. So, one term is r 0 I see. How about the first term? So, first term, let us see what it is. Mod square means this expression times its conjugate. I will not work out those, because very similar steps were worked out few minutes back. So, this quantity times its conjugate. So, there will be 4 terms, 4 product terms. First term will give rise to what? X of t plus tau prime times its conjugate, that will give rise to nothing but R 0. Similarly, another term x t plus tau into x t plus tau star, that will again give rise to R 0. So, there will be 2 R 0, 2 R 0, and then there are 2 cross terms. One of them will be what? X of t plus tau prime into x conjugate of t plus tau, that will give rise to autocorrelation at a lag tau prime. Other cross term will give rise to autocorrelation at a lag again tau prime, but conjugate of that. Okay. So, that means you will get twice, this you can verify, real part. Remember, z plus z star is twice real part of z. I repeat again, if you consider this, because what are the cross terms? One cross term is maybe I work out here. One cross term was between these two times x t plus tau, and this guy is conjugated, expected value of that will give rise to what? R tau plus tau prime. Other cross term will give rise to conjugate on the first. So, x t plus tau, not conjugate, but x star so, it is nothing but previous thing, but its conjugate value. So, complex number and its conjugate is nothing but twice real part of the complex numbers. That is what I write. And sorry, this will not be tau plus tau prime, if you, this is only tau prime. Because the lag here you can see, in one case t plus tau prime, another case t plus tau. So, gap or lag is only tau prime. So, these are purely tau primes, Okay, so, to real part of R tau prime. What is the implication of this? We will see. It actually shows that R tau is a continuous function, because I have to very soon do some integration involving R tau. So, it establishes the condition. Okay. Firstly, suppose R tau, whatever it is, at tau equal to 0, suppose it is continuous at tau equal to 0, that means given any number real number epsilon greater than 0, however small, around 0 you can find a range, maybe plus delta minus delta, so that when you are within this zone, then the gap between R 0 and R tau, this range, this is within epsilon. Okay. Epsilon may be very small. What is the meaning of continuity? However small the number you choose, however small, very close to 0, infinite very small. Still, around the point where I am looking for continuity, if it is continuous there, around the point you can find a neighborhood, say plus delta minus delta, however small again. So, that if you are anywhere within that neighborhood, then the difference between the function at that point and at that, or say the center point 0, that will be less than, its magnitude will be less than epsilon. That is, generally speaking, around the point of interest, that is 0 in this case. Okay. You can find a small neighborhood, however small, where all values of the function are very, very close to the function at, say, the center point 0. Very close means within some limit of epsilon. That is the definition of continuity. Then we say it is continuous. Now, this means you see this left side, that if it is continuous at tau equal to 0, Firstly, R0 is positive, we know, and if it is continuous at tau equal to 0, that is we are say plotting not R tau, because R tau is complex, I should rather plot it R mod R tau, okay, then only I can do one plot. So, we are plotting say mod R tau and R0 and mod of R0 they are same, because R0 is a real number. So, mod R tau is a function which is continuous, suppose it is given to be continuous at tau equal to 0. Okay. That means, at around tau equal to 0, I can find a neighborhood where all the values of this function mod R tau are very, very close to mod of R0, or that is simply R0. Very close means within epsilon, for a given epsilon however small. If that be the case, then what does the inequality say? That for any other point, say tau, not at origin, but tau, there also if I choose this tau prime, say tau prime, okay, within the range delta and minus delta, if I take, because tau prime here was varying within the range delta to minus delta, tau prime, okay, and continuity, it was going to be continuous. So, this right hand side was this R0 minus real part of, okay, one thing I forgot to mention, that real part of any number, complex number z is less than equal to mod z, because what is the real part of any complex number? So, z, if the complex number is z, what is the real part? Mod z cosine of the angle, and cosine of the angle is less than equal to 1. So, this is obviously satisfied. So, this right hand side inequality, in fact, I should modify to the following, noting that real part of R tau prime is less than or equal to mod of R tau prime. I can write this as R0 twice R0 minus mod of twice mod of or R tau prime. Maybe I write it somewhere else, because it is becoming a bit congested. I take the 2 common, then R0 minus mod R tau prime. Okay. And if I come back to what I was discussing, that suppose R tau is a function such that mod of R tau is going to be continuous at origin tau equal to 0. That means, given any small, however small epsilon, however small it may be epsilon, but a real number greater than 0, you can find out a neighborhood of size plus minus delta around the center point of interest, that is tau equal to 0 here. So, that for any tau prime within that range, the function R tau prime, its mod value remains close to, very close to R of 0 within a limit of epsilon. Okay. That is for tau prime, mathematically for tau prime in the range, tau prime in the range, this is satisfied that R tau prime and R 0, difference of that, mod of that will be less than epsilon. You can find out such a delta, however small that neighborhood would be. Now, it is given. That means, from this inequality I can see that right hand side is less than epsilon, and epsilon can be made very small. So, this product also can be made very small. So, that means, left hand side also can be made arbitrarily small. So, for if I now move to some point tau and go, I mean take the neighborhood from tau plus delta and tau minus delta, within that neighborhood also, that is why if tau prime, as I told you, tau prime is varying from minus delta to delta. So, within that neighborhood, also this function mod or tau, that function will be very close to the center point. Okay, that is, say r tau, let me write mathematically here. This means this at center point r tau, the difference between them also should be very close to some epsilon and epsilon prime. So, that means it is continuous there also. Okay. Now, for all our purposes, I will assume that r tau is such a function that mod r tau is given to be continuous at origin, and therefore, it is continuous everywhere. Under such case, I now define one quantity, there is a Fourier transform of analog Fourier transform I should write phi x x here. If I put x x, just once I will do, so that you know what it is. Capital omega is the usual analog frequency radian per second, and this is the Fourier transform. Fourier transform existence means that sufficient condition is that r x x tau must be absolutely summable, that is mod r x x tau integral should be finite. We are assuming that is to be case, so this integral exists. This quantity is called the power spectral density or power spectrum of the random process x t. Okay, why power spectrum, how is it related to power, all those things will come later. But obviously, if it is a Fourier transform, we have got this thing, the other one is inverse Fourier transform, that is given the power spectral density, okay. Now, consider this power spectral density function. My first claim is, it is a, even though r x x tau could be complex, and it is a complex integral because there is a j factor here, this phi x x j omega is a real function. Number 1, phi x x j omega real function, real valued function actually. Why? Because I can write the integral, divide the integral into two parts. One is from 0, or we can say 0 plus to infinity r x x tau e to the power minus j omega tau. Another will be from minus infinity to 0 minus, same thing. Okay. Now, here replace tau by minus tau, or okay. That means integral limits will be from plus infinity to 0. When tau is minus infinity, minus tau is plus infinity to 0. D tau will be minus d tau now. So, there will be a minus sign outside the integral. So, minus and integral from plus infinity to 0, two can be combined, so that minus becomes plus, and integral instead of from infinity to 0 becomes 0 to infinity. So, both the integrals then have limit from 0 to infinity, 0 plus to infinity. Okay. Only problem is you get r x x minus tau and e to the power plus j omega tau. Okay. That means what you have is 0 plus to infinity r x x tau, there is one term, another one is r x x minus tau. Now, remember r x x tau is r x x star of minus tau. Okay, r x x tau, we had this relation r x x tau as r x x minus tau star. That means r x x minus tau is r x x tau star. Remember that. So, I can write r okay. and e to the power j omega tau d tau d tau. Yeah. Now, you see if this quantity you call z, then the other quantity is simply conjugate of z r x x tau. So, r x x star tau e to the power minus j omega tau, e to the power plus j omega tau. So, z plus z star is always real, is not it? So, this is real even when the process is complex valued, correlation is complex valued. This is number one property. Further, for the special case, if x t real, then power spectral density phi x x j omega is not only real, because this is real always that you have seen, but it is also even function. Even means whatever is value at omega, same value you have at minus omega. That is not very difficult to see. In fact, I mean the what is phi x x j omega after all? It is a Fourier transform of a function r x x tau. So, if the function is real valued, for any real valued function its Fourier transform is even, we know. That is not difficult to show. If you are still insistent, we can easily see this is equal to what? R x x tau e to the power minus j omega tau d tau minus infinity to infinity. So, what is phi x x minus j omega? Minus j omega means everything else remains same, it becomes e to the power plus j omega tau. Okay. And then entire thing can be written as minus infinity to infinity within bracket r x x tau, because it is real, again minus j omega tau d tau, and then a conjugate. Conjugate, if you bring in r x x tau, its conjugate will be the same thing, because it is going to be real, and e to the power minus j omega tau, it becomes e to the power plus j omega tau, that corresponds to minus omega. And what is the quantity within bracket? That is phi x x j omega itself. And phi x x j omega star, but phi x x j omega is a real function. So, its star and itself are same, which is phi x x j omega. So, it is an even function. Why it is called power spectral density? Now, if you see r x x tau, that inverse Fourier transform we have seen. So, for a special case r x x 0, which is also power sigma x square, by that relation 1 by 2 pi minus infinity infinity phi x x j omega, then the other term was e to the power j omega tau d omega, but tau is 0 now, that is our choice. So, e to the power j omega 0 d omega, and this is equal to 1. So, you can as well remove it, there is 1. So, you see this gives all the information that okay, phi x x j omega is such a function, real valued function, that when you integrate it over the entire frequency range, then you get the average power of the signal. So, that means the phi x x j omega gives you an idea of how the power is distributed along various omegas. Okay. That is what is called power spectral density. That is between two frequencies omega and omega plus d omega, net power is phi x x j omega d omega. So, total is integral. So, once again I repeat, this gives an idea of, this is what the integral gives you, the total power, average power. Okay. And that means phi x x j omega is what? It gives you an idea about how that average power is distributed over omega. That is why it is called power spectral density. Okay. This is very important. What will be the unit? Unit of power is watt, and omega is radian here, radian per second. Okay, radian per second. So, what will be the unit? You work it out. It is actually watt per radian per second. If instead of capital omega use the frequency f, that is hertz, okay, then this becomes watt per hertz. So, the per frequency how much power, and then you integrate over all frequencies. Okay. This for power spectrum. A similar treatment exists also for the discrete time case. Similar treatment exists also for the discrete time case. Maybe we carry out the discrete time case later. Okay, today we concentrate still on this this case only. Now, suppose an x t WSS, it goes into a system, linear time invariant system of impulse response H t. Output is a random process y t. First, is y t WSS? Answer will be yes. What is y t? It is a convolution between h and x. H tau x t minus tau d tau. So, obviously, E of y t is E of this, and you can be expected say linear operators. The expression can be brought inside the integral. H is not random. So, E will operate only on x, and E of x t minus tau is nothing but the mean of x, because x is WSS. So, the mean of the process does not depend on what time you have, what time variable you have here. So, it will simply be h tau expected value, that is mu x independent of time d tau integral. So, once you integrate, tau disappears, you get a constant number. So, again mean of the output also is constant, does not depend on time. So, it is stationary with respect to mean, you can call it mu y. Now, you consider the case with correlation. R y y say between 2 points t and t minus tau. Or maybe let us find out this first. E of y t, say y star, is it a function of tau alone? Then it is stationary with respect to correlation also. So, let us find out. Y t will be one convolution integral, so will be y star t minus tau. So, there will be double integral. I am writing the double integral directly. Y t will be say h alpha x t minus alpha integral with respect to alpha, and y star t minus tau will be h beta star x star t minus tau minus beta. Here the time of interest is t minus tau. So, convolution variable is beta. So, h star beta x star because y star is present here. So, and integral is with respect to alpha beta. You push E inside because of linearity of this E operator. E will work directly on the product between x and x star, because H is non-determinate, H is non-random. So, you have got E of d alpha d beta, and you see what is this product, expected value of the product is a correlation. Input is WSS. So, this correlation depends on what? Only on the lag between t minus alpha on one hand and t minus tau minus beta on another hand. So, the difference between them, if you take out, t goes. So, here this quantity is nothing but r x x tau plus beta minus alpha, and beta and alpha after you integrate disappears. So, everything becomes a function of tau alone, which means output autocorrelation also is a function of the lag tau. So, it is stationary with respect to your correlation also. So, that means output also is WSS. If that be so, then what is output power spectral density? Because remember power spectral density needed WSS assumption, that is the correlation should depend only on tau, and then only you take the Fourier transform with respect to the tau. If it is not stationary, there is no question of power spectral density. Okay. So, station WSS nature is must, the correlation should depend, autocorrelation should depend only on one variable tau, and you take Fourier transform with respect to that variable. Okay. and that is what is happening on the output. So, output is, so I can find out the output Fourier output power spectral density. What is that be? What will that be? Simply you remember this result. This is the autocorrelation of output. So, what is phi y j omega? It is r y tau e to the power minus j omega tau, okay, d tau Fourier transform. R y tau is this double integral that if put here, it becomes a triple integral, and the all the integrals exist. If we assume all the integrals exist and therefore converge, you can interchange the order of integration, that we know, we have done it plenty of times. If you do that, let one integral be with respect to h alpha, another with respect to beta, and the inner integral, all are from minus infinity to infinity, inner be with respect to tau. So, r x x whatever has tau, that will remain inside, tau plus beta minus alpha times this e to the power minus j omega tau. Okay. Okay, just I know 5 minutes are left, so I will be doing soon. So, this is minus j omega tau. Suppose I write that as this tau plus beta minus alpha. So, to cancel out those extra terms, I bring in, so there is a star here, okay, e to the power j beta tau here, d beta, and e to the power minus j alpha tau here, d alpha, and this is d tau. First quantity is the Fourier transform, this is a transfer function h j omega, Fourier transform the impulse response. Next quantity is take the star out, so h beta e to the power minus j beta tau, that integral is again h sorry, this is not tau, there can be tau here, this is omega. I was hurrying. So, omega alpha omega beta, omega beta. Okay. So, what is the second integral? Second integral you take star out. So, h beta e to the power minus j omega beta, that is again h j omega star of that. So, h j omega h star j omega, and here in the inner integral, if you call tau plus beta minus alpha as some variable tau prime, so it is simply integral limits remain same, everything remains same, it is just a Fourier transform of r x x tau prime, which is nothing but power spectral density of the input. So, phi x x j capital omega. So, mod, this is a very important equation. This gives rise to the idea of filtering, that okay, you can design a filter, a system, so that given any arbitrary, given any power spectral density phi x s j omega, you remember this is a product relation. So, output power spectral density can be shaped by your choice of the function, that okay, input power spectral density is like this, but I want at certain ranges of omega its value to go up. So, I design a system whose values, whose mod value of this function actually is much higher at those ranges of omega, and I want that this power spectral density have much less value in certain other ranges of omega. So, I design the system such that at those ranges of omega, the value of this function, this is a transfer function, okay, h j omega is much less. So, that is actually filtering, that happens because of the product relation. You are directly multiplying one function by another function. So, by designing the second function, this h j omega appropriately, you can give a new shape to output power spectral density. That is the idea of filtering. Okay. So, I stop here now. using this relation we will show that this phi x x j omega, even for whether it is a real valued process or complex valued process, power spectral density is not only real, but also non-negative. We will show that. Then we will take up some examples of how to compute power spectral density of certain famous processes. Then I will move to a similar trade bait for discrete random sequences, what is its power spectral density and all that, and then we will go for estimation of those spectrum. I will relate the power spectrum or power spectral density of discrete processes with their analog counterpart, because when I do digital spectral estimation, I can only look for discrete sequences. There is a discrete sequences, not continuous valued. Okay. So, that is all for today. Thank you very much. Okay. So, last time we were discussing the spectral analysis, we defined what is called power spectral density. Of course, we are dealing with this continuous systems, analog systems. So, we just start from there once again, it will help us. So, suppose there is a analog random process, analog or continuous time. So, I just today I put a subscript A just to denote there is an analog signal x a t, let it be a random process, analog random process, and it has a correlation R a say t, R a tau, which is okay. And what is the power spectral density here? Phi a j omega is equal to maybe I change the notation a little here. So, I put R x x here. It is assumed, since I will be dealing with only continuous time case or analog cases only. So, even if I put R x x and do not mention any a here, it is assumed that I am still considering an analog or that is continuous time random process. So, similarly, here phi x x j omega, which we know is a Fourier transform of the autocorrelation function R x x tau, that is e to the power minus j omega tau d tau minus infinity to infinity. We have seen that even though the random process is complex valued and therefore, the correlation is a complex valued function, the power spectral density is a real valued function. Okay.